so we can get started. So this morning we have Daniel Hall, Jay Casbury, I may have mispronounced that, and Steve Gaw, who are going to give us the basics on transmission, as there's a lot of conversation about transmission. And those of you who remember Daniel, he was chair of the Missouri Commission and has been active in NARUC, and he's now working with, he is the Central Region Director for Electricity and Transmission Policy for American Clean Power, which is right there on the screen. So I'm going to turn this over to Daniel, and he's going to introduce Jay and Steve and then launch into our discussions. So we'll have some time at the end for questions. And thanks all of you for joining us today. Take it away, Daniel.
Thank you, Chair Rendell. Good morning to you. Is my video showing here?
It is.
Great. Good morning to you and to members of the Electricity and ERE committees. We are very excited to present to you today on a very important and timely topic, transmission. As you know, while transmission planning and development are predominantly under federal jurisdiction, state regulators have a vital interest and a shared responsibility in assuring resource adequacy, reliability of service, and affordable rates, all of which require a transmission system that can move power from where it is generated to load pockets in the region in a reliable and cost-effective manner. Let me take just a brief minute to explain why this topic is so important to us. We are witnessing a dramatic improvement in wind, solar, and battery storage technologies. Over the past decade, wind costs have decreased 70%, utility scale solar by close to 90, and battery storage in excess of 80. So analysis that takes into account all operating and capital expenses and factors out subsidies show that utility scale solar and wind are now the cheapest energy sources available. That development, along with increasingly aggressive state renewable standards and utility renewable targets, together with accelerating corporate demand for clean energy, explains why 90% of new generation looking to interconnect to the grid and RTOs across the country is from renewable sources. However, in order to bring that low-cost renewable generation online for the benefit of your ratepayers, significant new transmission is needed, which is exactly why we are so interested in this topic and so excited to delve into the basics of transmission with you today. We have two national experts to present. First, Jay Casbury, an engineer with over 40 years of expertise in the industry, including 20 years with SPP. We'll discuss the basics of the bulk power system, how it has evolved, and how the current transmission system functions to connect generation to customers. Next, Steve Gaw, who served on the original regional state committees in both MISO and SPP while chair of the Missouri Commission, and has worked for 15 years in SPP in the stakeholder process on behalf of renewables, will outline the transmission planning process and its role in furthering reliability, economic, and public policy goals. With that, and in light of the amount of information we're hoping to convey to you in this short period of time, I will hand the microphone over to Jay.
Thanks, Daniel. Let's move forward to the next slide if we can, Will. Thank you. And it's a privilege and an honor to be here. And I hope you learned something today, and I hope we have a really robust discussion at the end of the presentation. If I say something that confuses you, please interrupt me. I have a habit of using a lot of acronyms, and I apologize in advance if I do. So I'm an engineer. I started off doing transmission planning at Illinois Power in the 80s. And I wanted to get back into transmission planning in the early 2000s when SPP was standing up their RTO. And it's been a great ride. It's been a great industry to work in. Some things have changed a lot and other things have not in this industry. If Thomas Edison came back today, he'd see and he'd understand how this grid works to a large extent. But I want to go forward and go through some basic overview slides and then tee up some conversations so that Steve can take us through planning. Let's go forward, Will, please. So I'm going to give a real simple overview, and I hope it doesn't offend anybody. But, you know, electricity works by moving electrical energy from a generator to a load. And that's according to the laws of physics, right? Ohm's law, Kirchhoff's law. And in the past, you know, power has always flowed from large central stations to loads through distribution wires. Over time, they became transmission wires, then transmission networks to get to end-use customers. Things have changed recently with technology, with customer choice, with a lot of things on the distribution side of the system that now affect the transmission grid and vice versa. And we're going to talk about that some more, but let's go forward and talk about some basics here. Electricity is one of the few commodities you cannot store. So Will, if you go to the next slide. So there always has to be a balance between the supply and the demand on an interconnected network. And it's important that these metrics are in balance. Otherwise, the frequency is going to increase or decrease. If you have a huge amount of new load that pops onto the system, maybe some arc furnaces are starting up, or a big generator trips, there's an imbalance and the frequency will decline on the system. And fortunately, there's a lot of mass out there and inertia and governors that will respond from the old traditional thermal units that will bring back convert some of the kinetic energy into spinning mass to actually get the grid back to 60 hertz. You know, if we have significant imbalances, at some point we will actually curtail load, and they have under frequency volt load shedding programs, and those are implemented more times than not than I'd prefer. But to a large extent, you know, there are some large pump storage facilities in the U.S., but the geography doesn't support that a lot of where you'd want to have it. There are a lot of new battery projects that are able to store electricity, but to a large extent, you cannot store a lot of electricity on the grid. So you have to balance the supply and demand in real time. Let's go forward to the next slide, Will, if you don't mind, please. I want to give a bit of an overview, and this is a very old graphic here. It's actually a FEMA representation of the electric system, but it's a very old one. It's actually probably 15 to 20 years old by looking at it. And this shows the different voltage classes on the system. You can see a significant amount of 138 kV system in the Oklahoma and Texas areas of the system with that dark color there. But you don't see a lot of the more recent additions of the 345 kV that's been built into the Texas Panhandle from ERCOT to harvest the renewables, as well as the big projects in the plains by MISO and SPP to build lots of 345 kV lines from remote renewable sites to load centers and basically the rest of the grid, which used to just basically stop west of Interstate 35. But this is a map, and it is representative of a very complex machine. There are probably 7 or 8 voltage classes that have evolved over time, been built out to create this network. And there's actually 3 grids in North America. Actually there's 4, but 3 in the US. We'll talk a little bit more about that later. But the power system is very robust in the upper Midwest, for example, where you would expect it due to loads and due to generators. But the transfer of power, you know, from a point A, from a generator to a load can be more than thousands of miles. And all of the generators and all of the loads and the motors that are turning air compressors or pipe piping pumps for pipelines and things like that. Those are all operating at 60 hertz. So if there's a disturbance on any part of the interconnected system, you're going to see it somewhere else. It may be dissipated to a large extent, but it will reverberate until the system gets to a new balancing point. I didn't provide any animations, but there's plenty of them out there that show what happens when, like, the Turkey Point nuclear unit in Florida trips and actually sends, the frequency perturbations that are pretty extreme up in the northern plains of the US for several seconds. So that's an overview of the system. It's very complex, and it's a man-made machine that's one of the greater engineering achievements of the last century. I think what we need to do is start thinking about what we need to build for the next century. Let's go forward a little bit. I want to talk real quickly about, this is a very simplistic diagram. And in the past, the power always flowed from the left to the right. It always went from central stations where you'd have the coal or the gas or the hydro resources being the fuel, as well as nuclear and other things, up through a step-up transformer to get it up to a higher voltage where it's much more efficient to move the energy over long distances. Back in the turn of the century, the 1900s, there was 11 kV was a transmission voltage. And now that's a pretty small distribution voltage. So, but these long, big transmission lines have been networked over the years, and the system has evolved. And then it's eventually going to step it down to serve sub-transmission customers, big institutional loads, large factories, and eventually work its way down your back alley into your house at 120 volts or 240 volts. But that's the power system of the past. The new power system of today has lots of distributed resources, demand response programs, storage assets that are on the behind the meter, typically of the wholesale meter, and have implications to the bulk power system of the future. So we need to figure out how to make those systems work better together, to be more efficient and cost effective, reliable, as well as resilient, be able to deal with extreme weather events like we've seen recently. Let's go forward to the next slide. I think this is a graphic that shows how the system has evolved over time. Back in the days of Thomas Edison and Nikola Tesla and the war of the currents, trying to figure out, do we want an AC system or a DC system? It turned out that AC made sense. It's much more flexible. There's easy ways to transform it. You can tap it, all across the system. Not like DC, which requires some pretty big investments in converter stations. But you can see how the voltages on the system have increased over time. And most recently in the 60s, we went, basically in 1953 was the first 345 kV line, and that's important on the next couple slides. So that started by AEP, and then we built up a 500 kV system primarily in the Southeast as well as in the Western US. And then a 765 kV backbone was started by AEP in the 60s. Transmission system has evolved a lot. It's grown a lot, but we're not seeing a bunch of new growth because primarily of just efficiency programs and conservation efforts and demand response programs. Getting loads engaged in the markets and the operations has a major effect on their contribution to peak system requirements. But you can see on the bottom that, we had isolated facilities, whether it was the Pearl Street Station in New York serving Lower Manhattan. Eventually, those systems became more and more integrated and expanded, and then eventually regional and interregional systems. But we still have 3 separate grids in the US, and we'll talk a little bit about that in the next few slides. The next slide I wanted to show you was kind of the backbone transmission. I'm sorry, I got one more. Just want to make sure it's clear that, and we referenced the Kirchhoff's law and Ohm's law and things like that, the physics of the system. AC power flows make up the majority of the transmission capacity in the US, and that power is going to flow on the path of least resistance. So if you've got parallel ultra high voltage or extra high voltage lines, maybe a 345 kV line in parallel with an aging 50-year-old 138 kV system, there's going to be a lot more flow on the 345, but should that EHV backbone line go out of service, the flow is going to transfer on the underlying 138 and probably create problems if the system hasn't been planned appropriately, or if weather patterns are extreme to drive super high loads, or generators are out of service for whatever reason. But the AC networks are generally meshed, and absent controls, the operators really can't force electric power to flow on any select path from a resource to a load. Now that's changing with things like power flow controllers and phase shifting transformers and phase angle regulators. There are new fax devices that help us control the power. And I think they're going to be a bigger part of the grid of the future. But AC power flows on the path of least resistance. And let's go forward to kind of the backbone grid we have today in the US. This shows the 345 kV system, as well as the 500 kV system and some 765 kV, as well as some big DC projects too, DC links, and you're seeing more and more discussion about those. But it also shows the back-to-back DC ties between the East and the West grids, as well as the Eastern interconnection and into the ERCOT markets. That's the grid we have today and what we're trying to optimize going forward. On the next slide, you can see that, and this is a slide from NARUC, the North American Electric Reliability Corporation. And it's indicative. I don't know if it's exactly correct, but it's indicative of aging infrastructure. And these lines here are 345 kV lines that were installed and higher, 500 kV even, as well as 765 that were installed in prior to the late 70s and the oil embargo of 1978. These assets here are aging, and many of them are in need of replacement and approaching the end of life. That's the acronym there, EOL. To me, these lines represent some of the critical corridors that could be used to increase the connectivity and the capacity of the existing system without imposing new projects that need regulatory approvals and need permits and siting and all the challenges of building new greenfield transmission projects. So to me, this is low-hanging fruit when it comes to looking at ways to make the grid more efficient, especially interregionally and within regions. Go forward, and I'm going to wrap this up in a couple more slides. So this is a map that shows the existing interconnections that exist. And I guess it's important to note that there's not a very strong grid in Canada. The actual Canadian provinces have very strong connections to the south into the US. A lot of that is for exports of hydropower in Vancouver, in British Columbia or Ontario, Quebec, south into US markets. This shows the grid that exists today and has been that way since the 60s, basically. Back in 1967, they tried to synchronize the Eastern and the Western grids, and it wouldn't stay together because the thermal mass and the size of the units in the Eastern grid were about 4 times the size of the units in the West. So anytime there was an outage in the West, 80% of the energy would flow from the East to the West to help restore balance to the system. And that would trip out relays and lines. So they ended up putting in some DC ties that have been there since the 70s. And we need to probably figure out what to do with some of those in the long term. Let's go forward if we can. This is just a timeline of when and what happened to drive regional transmission expansion at FERC. There was some regional transmission group policy and transmission pricing policy statements back in the mid-90s that led to FERC Order 888, which was a big thing for the transmission system and changed how utilities operated and what their responsibilities were going forward. Then FERC Order 2000 came out that encouraged regional transmission organizations in 1999. Then they got into the planning functions with more and more granularity with Order 890 in 2007 that established the minimum planning requirements for all regulated utilities. Then 2011 came out with Order 1000, which did a lot of good things in terms of regional planning and putting some guidelines around regional cost allocation, eliminating the right of first refusal, which created some challenges, but really didn't never promote and result in any major interregional transmission expansion, which was something I think we're going to need going forward. Let's go forward, please. Next slide. Just a nice graphic to show the difference in the load zones, as well as the resources, the renewable resources, whether they're hydro projects, whether it's the solar projects, which are primarily the best quality in the southern US, particularly in the desert Southwest, as well as the wind resources. The offshore wind is very high quality in the Northeast and Eastern Seaboard, as well as off California, Northern California. But the majority of the wind development to date has been in the plains of the US, as you might expect, from Texas up into the Dakotas, and over into Wyoming and Colorado and New Mexico, just because it's such a high quality resource, but it's very remote. Big thing about our US system is we've got time zones and we got weather patterns that cross many days. So the wind's going to be blowing somewhere all the time, but we don't have transmission that allows us to take advantage of that today. Particularly if you look at what people are wanting to do in the next 10 to 15 years, if we're going to need 2 to 3 times the amount of transmission capability to move renewable energy across time zones and move with weather patterns, we need lots of new transmission. So let's keep going forward. So recent studies have shown the needs to, add 2 to 3 times as much transmission capacity from coast to coast. This is the Princeton studies, the work coming out of Vibrant Clean Energy and others, as well as the SEAM study, which is shown on the bottom left. The flows that you would see if you actually had a copper sheet across the US would be significant under a high renewable scenario where you had a lot of solar projects in the desert Southwest and a lot of wind development in the plains. That's what the patterns you see on the right, where you see 20 gigawatts of power flowing at night from the Midwest to the West Coast, and then it flipping back in the solar power during the morning in California and Arizona, moving east to serve the load centers in Chicago or Atlanta. And you see that every day, but we don't have a grid that can do that, but I think we need to consider how we could get there through the macrogrid or whatever initiatives are in the work. Let's go forward if we can, please. So one of the things that we've talked a lot about renewables and trying to get clean energy to markets, and that's during normal system conditions. One of the big things you see about the benefits of major transmission is during extreme weather events. And this is the LMP prices when PJM was trying to export a lot of power to the west through MISO and then into ERCOT. And you can see the price spreads on Western PJM into the MISO load centers in Illinois, Missouri, right during the event. Excuse me. You'll see here that MISO was importing about 13,000 megawatts of power at this snapshot in time. At the same time, ERCOT was importing about 800 megawatts, which is the limit of their DC ties with SPP. Shortly thereafter, those ties were cut because SPP was short. But you can see that there was a big desire to move lots of energy from east to west. That's never been in the planning horizons or models, but it happened, and need a system that can be resilient and respond to these events. In the next slide, you'll see the actual flows between major regions. You can see that SPP was importing about 5,000 megawatts from MISO, and MISO was importing 10,000 megawatts from PJM, and how those flows changed over the times. But this is just some great data. If you want to get a feel for when things happen, you can see that as schedules got cut, that that was when the load curtailments actually happened to a large extent and were extended over time with due to other factors, primarily lack of gas supply and gas resources and extreme cold weather. Let's go forward, and I'm going to wrap this up, hand it over to Steve. But what we've talked a lot about the big transmission system, and I really think we've got to find a way to take advantage of the latent capacity in the existing system, as well as the system that we've actually got approved and in the works in the near term. And I'm a big fan of grid enhancing technologies. You know, you've heard of dynamic line ratings, and due to recent FERC, workshops looking at the benefits and potential shared savings for grid enhancing technologies. But topology optimization, I mentioned, advanced power flow controllers, storages, transmission. These things can be installed relatively quickly at a very low cost. They can be redeployed as congestion moves. They're scalable and modular. I'm a big fan of grid enhancing technologies as a way not only to help us deal with the rebuilds and the extended maintenance outages of transmission lines that are getting old, because we know we're going to have congestion for extended periods of time. We can deploy these technologies and manage the grid better than we would absent them. So with that, I'll turn it over to Steve.
Well, good morning, everyone, and it's a pleasure to be here. I hope that everyone knows how much we appreciate NARUC. Those Daniel and I both experienced how great this organization is for commissioners and staff, but it is also a great way of communicating about the industry as a whole, and just appreciate this opportunity to be here.
How are you?
Go ahead and
I'm on a
advance.
web.
Will. Yes, that's not Mahatma Gandhi, but the quote is from him. And I think all of us would love to be able to go back in time as we got to watch with the 3 Back to the Futures and change what we would have done if we had only known where we were headed. Go ahead and advance the slide. So that's why we plan, because we can't go back and change the past to adjust for our future. I love this quote from Eisenhower, in part because everyone is always perplexed about how it seems to be a contradiction. If you think about it, though, it really makes a lot of sense. Planning is extremely important, but in the end, as you often hear whenever you're in any of the planning regimes of any of the RTOs or the other places, we're never right. So why do we plan at all? Because we're trying to be prepared to the extent that we can for the best possible outcome based upon what we know and what we believe is going to be the case. And by doing that, we should be better prepared and hopefully be able to be flexible enough to meet those things that we do plan for. And if you look at where we are in transmission planning, that's exactly what we're trying to do. Go ahead and advance it, Will. So why is planning particularly important for transmission? Well, it takes a long time to construct it. And if we don't construct it with an idea of where we're going, it's going to potentially risk reliability, and it also can cost money. We know that generation additions and retirements in today's world particularly are occurring at an increasingly fast pace. We also are aware of the fact that public policy has over the last decade plus played an increasing role in what our needs are. And we're trying to look at all of those things, anticipate those things, and plan for a design that's flexible enough to encompass those needs. Go ahead, Will, go to the next slide. So again, this is about time. We have a lot to do to get this transmission up, including the planning portion, the authorization. In an RTO world, that includes the authorization to build, siting, which everybody, I think, on this call knows the challenges that can come about with siting. You need to acquire right-of-way. You have to do the actual construction. You've got all sorts of things that play into permitting, particularly in the West. And then, of course, there are things you didn't anticipate that you run into that frequently can cause delays. And particular projects that we have seen have run into significant delays because of things that can occur on permitting and other matters, including opposition to the lines. Go ahead, Will. So yeah, it's always the chicken and the egg thing when it comes to planning. Are we planning for what we have today? Or are we planning on what's to come? Go ahead to the next slide, Will. I love these quotes. I'll give Jay credit for the fact that he brought Gretzky up. You skate to where the puck is going to be, not to where it's been. And if you're Tom Brady or Patrick Mahomes, you're throwing the ball not to where the receiver is, but to where he's supposed to be. And that's the same thing that applies if you're out on the range with your shotgun. If you're looking at what you're planning for, you've got to define your needs, and you want, again, to be flexible enough to adjust your plans, or in this case, to have a system that's adjustable enough to take into account the fact that you cannot get exact on what those needs are going to be. And of course, you're trying to plan it with some sort of a cost-effective result in trying to make sure that you're looking after this from a consumer standpoint and that your investment is wise. Advance it, please, Will. So what are we talking about with transmission planning? Well, we got to figure out what our needs are. We got to figure out when those things will be needed. And then you got to calculate, well, how certain are we that we're going to need those things? Is this something we know pretty darn sure is going to happen, or is it something we think might happen? And how do you evaluate that need? What's the mechanism that you're utilizing to determine what those needs are? And then how do you come up with your solutions? What's the mechanism that you utilize to determine what you need to build or not build? Advance, please, Will. Real quick here, this is just a map. I think 90% of you or more have probably seen about the renewable potential in the US. Go ahead and advance, Will. The growth of renewables, which we've already talked about, this is particularly important because of the fact that it has changed what we need on the transmission system as we're in the middle of this revolution on supply and demand. Go ahead and advance, please. Of course, not only are we adding generation, but we're also retiring generation and anticipating a significant swath of retirements that could potentially have a major impact on where we're going on our transmission front and where that supply is located and how that supply is going to act when it's being dispatched. Advance, please, Will. So this is just a map of our planning regions. They have varying degrees of importance. And what I mean by that is in the sections that deal of the map deal with the RTOs, it's a different approach to planning than what you would see within the utilities that are located in the non-RTO planning regions. And we'll talk about that in just a minute. Go ahead and advance the slide, Will. So I want to talk a bit about non-RTO planning, particularly in trying to understand the difference between what the utilities are doing and what the plans are in those non-RTO regions. It really is more of the set of what you are trying to do as a utility to meet your load requirements with generation. You're looking to see whether or not you can reliably deliver the generation that you have to the load that you have, and in anticipation, not just of your current needs, but of what particular generation you may intend to add. And of course, you're not an island. You have to also understand how the flows of your neighbors are impacting you. The integrated resource plans that many of you all are involved in would encompass some of these kinds of things when they're brought to you. Not just the new generation that the companies think are the kinds of generation that should be added based upon their projections, but also potentially their transmission needs. These non-RTO planning regimes tend to concentrate on local planning. And again, reliability is primary, but also, you know, if I've got a generator that I can't deliver to in full to what I have on my load side, I would look to see whether or not it's a less expensive gen that where I might benefit from that lower cost fuel resource, or if I've got public policy needs that I need to deal with. And then there is this additional step, somewhat from order 1000, to look at, hey, if I have a regional solution for my local utility needs that can be met on a more cost-effective basis regionally, I would look at trying to construct that from a regional point of view instead of potentially from a local one. Advance it, please, Will. So now this is just a subset of the previous map. These are the RTOs that I think most of you know and love. So go ahead and advance, Will. So RTO planning. So RTO planning is a bit different, although a number of the characteristics are similar, and this varies from RTO to RTO. So don't take this as being necessarily the same and applicable across all of these footprints. But generally speaking, the market in those regions will determine the dispatch of the generation across multiple utilities, not just one or two. So we will look at the transmission limitations to determine whether or not that market dispatch can be made more efficient. Those transmission limitations are exposed and transparent in the market because they come across as a particular charge that represents the congestion that exists. So economics in the RTO world is particularly critical. Next slide, please. So RTOs did change the face of transmission planning on its face because of the fact that it is more regionally focused as opposed to locally focused. All three of the major categories would be looked at: reliability, economics, and public policy. Next slide, please. And so the primary way that most of the RTOs look to calculate economic savings from transmission construction is through adjusted production cost calculations. I'm not going to go into how these work, and they are not the same in every RTO. There are slight variations when they're looking at the economics, but generally you're looking at trying to access lower cost generation in the market by reducing congestion through paying for additional transmission. And the question is the investment in building that transmission, does it generate sufficient savings to the region to warrant that transmission being built? Next slide, please. So we're looking at whether we can get cheaper generation into the market by reducing congestion as opposed to whether or not there's more expense to it. But at the same time, we're trying to co-optimize both the generation and the transmission to get us into a better place, a lower cost position in a reliable way with transmission designs that would be added to the system. Next slide. So I did this slide just so you all could see what a brilliant artist I am. And primarily for the fact that I'm still trying to prove my third grade art teacher wrong. But in truth, I wanted to just give you a very basic summary of this construct. This is way simpler and probably somewhat inaccurate. But if you look to the left, you'll see I've got generation 1 and generation 2, G1 and G2, both of them generating up to 100 megawatts. The generation 1 in green circle up there is a very low cost generator. Generation 2, I've just said, is a medium cost generator. Those lines going out are interconnecting to a line that can carry the full output of both of those generators up to that line that goes up and down to the triangle, which is a load. I've labeled load 1 in that triangle, and that load can utilize up to 100 megawatts of that energy. So I've got an additional amount of energy there from generation 1 and 2 that could go clear over to the right if it were economic or if it were appropriate to serve load 2, which is also 100 megawatts. I've left these all the same to keep these simple. It is also tied into another generator, generator 3 over there in the square in gray, that is a high cost generator. What you can see there is if I am in load 2 and I could access some of that generation over there on the left, I could lower my costs of serving that load. But today there is only 50 megawatts of that generation on the left could be delivered to load 2 based upon what I've got on there. You see that 50 down there. The question becomes, what would it cost to add additional capacity? That's the dotted line or the dashed line down below. And would it be worth the value of increasing that capacity on that line in order to access that lower cost generation? That is the premise of everything that comes afterwards in regard to the evaluation. Now, if you look at this in a system, you're looking at thousands of generators and many transmission lines. So the analysis is extremely complex, and you don't just do it at one point in time. You have to do it over the course of the year, 60 hours over the course of the year. These adjusted production cost models are designed to look at. Next slide, please. So we've got reliability issues, and what you're trying to do is to solve them in the most economic fashion. In other words, how can I meet those reliability needs in a cost-effective way? Two subcategories I would say are under this category of reliability. One is resource adequacy. If I've got to have a certain level of generation that can serve my load, I want to make sure it's deliverable. Generally, then you also are looking at thermal and short circuit voltage issues on the system to make sure there are no violations. But the reliability of the system, especially on the resource adequacy basis, generally is a snapshot. And for a lot of the world, that snapshot is at peak for either the RTO or the particular load serving entities that are within the RTO or non-RTO area. So it's a snapshot of a certain number of hours. Generally, a lot of them are in summer peak. There's a real question of whether or not those reliability needs need to be evaluated beyond just that time frame, especially after what we've seen lately. I think it's highlighted during the winter event. Next slide, please. So public policy needs include renewable energy standards and others, and how are you going to meet those? Again, sort of like the reliability piece, you're trying to meet those in a cost-effective way. Next slide, please. In addition to the normal adjusted production costs and reliability pieces, there were a number of benefits that can be looked at beyond those that transmission can generate. I just listed a whole bunch of them there. We'll move forward because we're running short on time. Next slide. So what are the components of good planning? First, it's forward looking. It's not just about what we need today. It's both long-term and short-term. We're trying to match generation additions to the long-term resource requirements that you have to meet your load plus reserves. And you want to evaluate that over multiple futures, not just one, because we don't know what's going to happen. We're trying to figure out what kind of design would we need to meet the particular needs of a region or a utility over more than one possible scenario. So you're trying to come up with a design or upgrades that can meet more than one particular outcome over the next 5-10 years or so. Next slide. So you have to come up with futures, develop them. You have to calculate both your needs from a supply and a demand side, and also, determine what generation is cost effective, what kinds of policies, things you need on your gen side, and what kind of variance on your load side and demand side will come up. Next slide, please. I'm not going to spend any time on this. This is in the deck. This is an example of a Southwest Power Pool summary of some of the key things that you would have in a set of futures. This is just, I know it looks very complicated. This is just a one-pager. The description would take a long time to go through, but this is the kind of thing that you need to do when you're doing planning, both on an RTO basis or if you're looking through an IRP proposal. Next slide, please. So again, you're looking at your needs, you're developing solutions, and then you're coming up with a portfolio based upon the solutions that you think are the best for your futures. Next slide. So what do you do here? You're trying to figure out not just one thing. You could design this separately: solutions for reliability, solutions for economics, and solutions for public policy needs. But transmission itself, once it's built, facilitates potentially all three. So hopefully your analysis will include a design optimization that attempts to craft solutions that actually meet more than one need and take that into account in the design, avoiding just little additions here or there that don't take into account both the long-term anticipated needs that you have and doesn't segregate the solutions into these silos. Next slide, please. So again, you need a need by date. When do these things need to be built by? That includes what you're doing on trying to assess when you put anticipate these things going into the ground. Next slide, please. I'm trying to hurry so we can have time for questions, by the way. And then you want to optimize and consolidate all of the different information you have on the solutions, and in the end, come up with solutions and a portfolio of solutions or a set of solutions that work together with your existing transmissions system to facilitate an end result that optimizes all these things. We are doing that in many of the RTOs on the traditional planning side. What we don't have today, which we need to, in my opinion, move toward, is optimizing not just our transmission planning process, but also with that, our generation interconnection design and our transmission service designs in those areas that have that, so that we are trying to, again, create the best bang for your buck and the most flexible system we can for everyone that is served by that transmission system. Next slide. So just to say this, examples of this are in SPP and in MISO. The multi-value projects did that. The design phase of the SPP does that. And SPP is also looking at carrying that farther today through the script process. Next slide. In original planning, we've got a long ways to go here. Order 1000 just scratched the surface. We've got some going on with the TMEP's proposal with PJM and MISO. Thanks to many of the states in the SPP and MISO footprint, I give them huge credit for this. We're talking about this joint study that's going on with MISO and SPP today to help facilitate both interconnection and benefits to load. Next slide. And in the end, and we're not going to talk about this today, but it's really hard for me because I learned, and it was ingrained in me a long time ago, that planning and cost allocation do really go together like a horse and carriage. I mean, there is no way in my mind to separate those two. And maybe sometime in the future, if you all are interested, we can talk about how those two things come together. And with that, I'll close. I really appreciate the time today, and we'll open it up for questions, Ann, at your, or however you want to handle it. Thank you.
Okay, well, thank you so much. I really appreciate this. I've gotten some messages, some folks had to leave, but really appreciated the presentation. I'm glad we're recording this. So there is a question. Commissioner O'Donnell from Maryland did let me know that he has a question. And so if you would like to unmute yourself, and those of you who do have questions, why don't you use the raise hand function or send me or Will a note in the chat that you have a question. So go ahead, Commissioner O'Donnell.
Okay, can you hear me?
We can.
Okay, good. So my question for the panelists is, what is able to be done in the near term? I mean today, now, because I'll give you an example. In PJM, there was a transmission project, relatively short lines running from southern Pennsylvania into northern Maryland. It was the IEC Transource project, and one state approved the CPCN and conditionally, and one state rejected the CPN. So the project, I think, is effectively dead, even though we haven't seen the Pennsylvania decision quite yet, but we know what it is. And if we can't do a market efficiency project like that, reducing congestion constraints now, what makes the panelists think we can accomplish kind of the future vision of where we need to get to get all this done?
Yeah, I think this is Steve. I'll take a stab at that. I'm because I focus so much in the Midwest, I'm not particularly familiar with that line, Commissioner Saw. With that said, we really have a challenge here. I mean, planning is only one piece of the puzzle. I think many of you know that, you know, if all you're doing is planning and then the plan sits on the shelf, the plans don't mean a whole lot. It has to follow up with action and construction and dates that move things forward. And if you don't have that, it's going to be a problem. Transmission is of increasing importance in making the whole system work. It is clear that as we have expanded and we're changing our generation mix, that our interconnectivity across not just utilities or RTOs, but across RTOs is of increasing importance. I mean, so I mean, if you look at the event that occurred that Jay mentioned earlier during the winter event, the use of the multi-value projects in MISO, which were designed for west to east transfer, were incredibly important in saving a lot of customers from being out a lot longer than what they were in MISO and the Southwest Power Pool. If there'd been a gig of transfer capability from ERCOT to the southeast, some of the estimates say that line could have been paid for in less than 10 days.
Steve, hey Steve, can I interrupt you?
Yeah, go ahead.
Let's level set. We all know we need to do this. Everybody on this call knows we need to do it. We don't need to kind of keep driving that home. But my question is, we can't get simple things done right now. What makes us think we can get the big things that you guys are talking about done? That's really my question.
Yeah. Danny, you want to tackle that?
Sure. I'll take a stab at that. I mean, I think first and foremost, it takes identification of a problem. And I absolutely agree with you, Commissioner, that I think there is growing consensus that there is a problem with regards to transmission planning. But the next step is actually doing something. And I think that what's going on in both MISO and SPP recognizes that there's a problem, and they are making concrete steps to move towards some improvements. In MISO, the long-range transmission plan with the soon-to-be discussions on cost allocation are absolutely critical, and I think recognized by stakeholders throughout MISO. On the SPP side, as Steve alluded to, the script process where they are going through a top to bottom evaluation of planning and cost allocation and transmission service and transfers, and looking for ways to improve those processes. It's an extremely ambitious effort. Steve's in the middle of it. It's too early to tell whether it will bear fruit or not, but I certainly applaud the effort in that regard. And then also FERC has identified planning as an issue, and I think later this summer into the fall there will be efforts underway there to evaluate the planning process and consider changes. So stay tuned, stay engaged. We've got a lot of work to do, but I think there's a lot of people coalescing around some solutions.
Thank you for that. Thank you both for that. I will just say parenthetically that when these projects fail, when CPCNs are not issued for these projects, they're still very expensive to the ratepayers, and they pay for them for many years, even though they're never going to be used and useful.
Yeah,
And,
that's a very good point. And I think, Commissioner, to Daniel's point, I would love to see us figure out how the states and the FERC can address these problems together, because everybody is really important to this equation, right? And so I appreciate the fact that you're raising it, because you're absolutely right. We have to be able to do things in a bigger way than and if you can't move the small things, we got a problem we got to fix.
So Susan, Commissioner Duffy has a question, and I see she's got her video on. So go ahead, Commissioner Duffy.
Yes, thank you. And thank you everyone for being on here. These are very helpful for me. So following along the discussion we're having right now, how important is the administration, the Biden's administration infrastructure vision important to our discussion today? And what can we as commissioners in different RTOs and locations, if it is important, what could we be doing, as there are real dollars behind the infrastructure proposals? So does this really factor in, guys?
I think it absolutely does factor in. I think it could be a tremendous help, depending upon how the policy ends up being adopted. But we could potentially see the evaluation of a lot of transmission in a benefit cost analysis get a lot more favorable.
Okay, so who is going to do that? Is that FERC's responsibility to get the ball rolling on this, or is it each individual RTO putting their brains together? And
so I think it's important that the RTOs and those that are working on the national policy piece of this, particularly if we're talking about some sort of a tax credit to help incentivize some transmission here, that fit in with the RTO planning process. So it's taken into account when you're evaluating BC ratios. I also think if they get into any kind of proposal that allows us to look in, and that's an RTO and a communication problem beginning. From the FERC standpoint, I think FERC setting the something more than what they have today in Order 1000, particularly on the interregional side, would be very helpful. It's really a struggle on the interregional side under the current regime that we have. And we need a way, and I think FERC could help on this. This is to try to bridge over the needs in the generation interconnection side, the needs on the load side, so that we can optimize both of those needs together. FERC could help that process if they can help find some avenues to join that analysis and to look at how cost sharing could be done to manage.
Okay, so that said, do you believe the composition of FERC today has the aggressive nature to bring us all to the table to say, we need to start figuring this out?
I mean, I'll just speak for myself. I'll throw it to Daniel or Jay, but my belief is you're going to see some significant leadership out of FERC on this issue. I think the chair and the majority, and hopefully all of them together, will find a path to see that making this a priority and having something happen to fix some of the issues that are preventing us from seeing the things done that need to be done. Daniel, you want to
I'll
address
just
it?
say I 100% agree with what you just said, Steve. I think the message coming out of FERC recently is very supportive of trying to address the shortcomings of Order 1000 and a variety of other planning issues.
So what do we need to do as commissioners to make sure that folks, I mean, should we be talking to our congressmen? And I know there's a lot of resistance to this mega billion infrastructure plan, but should NARUC be taking an active position with all of this? I mean, what's your thoughts there? You
So-
guys have highly
I-
vetted.
So Commissioner Duffy, I appreciate this. Those of you who want to stay on, we're a little over time. Thank you for those of you who have to drop off. Why don't we spend a couple more minutes? I just want to say this is a precursor to a panel that will be at the summer NARUC meeting, again, talking about transmission planning. And those of you who have been watching the news know that FERC Chair Glick is working with NARUC leadership to try to bring together some way to have a conversation about transmission planning and the issues we're having in transmission. So I think there will be a role for the states. We need to, from my perspective, we need to make our thoughts known on this, either through the RTO state committees or in states that aren't part of an RTO, through our regional planning organizations. So with that, I'm going to turn it back over to Steve and Daniel and Jay if they have any final response to your question, Commissioner Duffy, and then I think we probably should wrap up. But maybe those of you that are going to the NARUC meeting can have a continued conversation about this. I'll turn it back over to you, Steve, and Jay for any final comments.
Thank you, Chair. I would say that in what you just said was very important. I think that NARUC and individual commissioners particularly those that would like to dialogue on this are going to have an opportunity to give feedback. And I really think historically, all of us have seen things that have happened that have been driven because the states have helped drive the conversation. And I think with that coupled with the interest we have at FERC, there is an opportunity for a partnership here of trying to solve some of these problems. And I look forward to that being the case. I think if we can get, if FERC hears support from the states on trying to solve this problem, it will make a significant difference in the ability to get those things done. And so I would highly encourage folks to stay engaged. As you have just said, I think it's critically important. And I think FERC will be open for that. And I think we've got an opportunity here that has not come along in a long time. Daniel or Jay?
I'll just piggyback on that and say I think FERC is looking for a partnership with NARUC and the states. They absolutely understand the vital role that you play in the process, and I encourage active engagement, and hopefully we can see some progress here.
Yeah, and this is Jay. I just echo that. I think we've got some challenges, but I think if we work together, we can solve anything. So look forward to the conversations at the next NARUC meetings.
Okay, so that's our call to action. Thank you very much to our presenters. We will be sharing more information. I'm sure Michelle is ready to get, Michelle Malloy is ready to get some emails out to all of you about the agenda. So stay tuned. And those of you on the electricity and ERE committees, thank you for attending today. And we will be posting this recording and sharing it with all of you shortly. So thank you very much and have a great weekend.
Thank you all. Thanks very much for the time.
All right.
Thank
thanks.
you.
Bye.
Very much appreciate it.
Good
Take
day.
care.
Thank you, Ann.